Hello guys, myself Meet Nagadia, and today we'll be doing one of the again deep learning projects which would be hand sign classification. We'll be using MNIST dataset which provides us with hand sign. So first of all, let's see what are the hand signs are. So basically this is the kind of hand signs. So this is not the actual images of the hand signs. This is just the pictorial representation of the hand signs. So basically, this is the kind of again, this is not the actual dataset images that we have. This is the pictorial representation. Let's talk about the hand sign. So basically, American Sign Language ASL is a complete natural language that has the same linguistic properties as spoken languages with grammar that differs from English. So basically, ASL is expressed by movements of hands and face. It is the primary language of North Americans who are deaf and hard of hearing and is used by many hearing people as well. So again, the dataset is formatted is patterned to match with closely with the classic MNIST, and here we have a training dataset as well as testing dataset, and each dataset have a label from 0 to 25 as to map one to one of each alphabetic from A to Z. But here we don't have J as well as we don't have Z. As you can see here, we don't have J as well as Z. So because of this, we only have 0 to 25. Now the training data set, talking about the data. So basically we have in training, we have 27,455 cases. Well, in test data, we just have 7,172 cases. So these are approx and half of the size of the standard MNIST. But we can see that the first row would be containing the label as well as pixel from 1 to 784, which will represent a single image of pixel value 28 by 28, and the gray one values are starting from 0 to 255. So the original hand gesture image data represented multiple users repeating the gestures, again different backgrounds. The sign language MNIST data comes from greatly extending the small numbers 1704 of the image color, including as not cropped and hand region of interest. So basically this is what the kind of hand signs look like. So this is again the image. So this is not the image of the actual hand sign. So before starting the project, this one, we need to understand that we are creating a deep neural network. So first of all, we need to check the data, what how the data look like in the training as well as the test, and then we'll decide what to do next. So here I am using I am using Kaggle Notebook. You can also use Google Colab or Jupyter Notebook or Anaconda for this. So I have enabled GPU here, and the preferences are just normal by default, and the dataset link will be in description. So we are using this dataset from Kaggle. So this is called Sign Language MNIST. So basically we have our train test, and these are the some sample images for the understanding purpose. This is the grayscale image, and this is just the again representation, drawn representation. So I will link this data set in the description, as well as you will get the notebook in the link description. So let's start. So our first step would be to import libraries. So here we'll be importing libraries such as CSV, string, pandas, numpy, TensorFlow, matplotlib for plotting, and then we'll use TensorFlow keras for image processing as well as creating our model. So we'll just run it. You can also find my other projects in the description where I have done Bitcoin price prediction. We have done detection of Parkinson using XGBoost, and also the digit recognition. So now let's move on with this one, and here as we can see we have successfully loaded all the imports. So now we'll move on to next one. So now this step is to actually load the data. So what will we do is we'll first check. So here we can see that in data we have input and we have just loaded our data set. So in data set we have sign mist test and sign mist train. So as we open SignMist, we can see that we have here CSV format of file and again CSV. So here basically we are given a data set where we don't have the actual images, but the grayscale image, or we can say the grayscale input, has been given to us of 786, that is 28 by 28, and we need to pre-process this data so that we can further move on with our image recognition. So first of all, what we can do is we can just load the directories, and then here we will be using test set as the actual validation set, and then we'll define some globals with the path of both the files. So we are just here loading the file. So what we can do is, how to get this on the Kaggle is just simply we go on to our dataset. So this is our dataset. Suppose this is how it will look. So we just go on test and then just copy this, and we'll just, let's say here we'll just paste it, Control V, and the same with the train one, go copied, and we can just Control V. So we'll just do that and we'll here run. So it is run. So now we'll load our data. So how can we do that? Note, unlike the other data set, this data set will not have the actual image provided, as we can see already. Instead, we have given the data serialized in CSV format. So taking a look at the CSV file, now we will actually take the file and will see the what is the header and what is the subsequent line. So we are just opening it with the normal file. So with open, then our file path. So we have initialized file training underscore file as our file for the train. So we'll just open as the training file, and line is equals to training line dot read line. So it will read the line, and then we are just printing the first line, like first line header, and then looks like this, and then the line, and we'll again read another line and we'll just print the subsequent line. So we'll just run it. Yeah, so here it is. So this is the label that we have, that is the header of the first line of the file. So it will be just containing the columns. So first column is label, and then we have pixel 1 till pixel 71784. So these are all the pixel that we have, and then we'll be having the pixel values for it. So the label is 3, and then we have the following pixel values. As we can see that each file includes the header, the first line, and then a subsequent data point is represented as the line that contains 785 values. The first value is the label, as we have already seen here. The first is the label, and then we have here 3. So if we see up, sorry, here, so it is representing a C. So the first value is the label, the numeric representation of each letter, and the other 784 values are the values of each pixel of the image. Remember that the original images have a resolution of 28 by 28, which sums up to the 784 pixels. So now what we'll do is we'll parse our data set. So how can we do that? We can simply create a function for it. It would be much easier. So for the later use also, we can just copy this function and we'll just paste there. So it comes in handy when we create functions like this. So what we'll do is we'll create a function that would be able to read the file that is passed to it, and as an input, and it will return two numpy array. One will be containing the labels and other will be containing the 28 by 28 representation of the each image within the file. This numpy array should be of type float64. So we'll create a function that would return us the two numpy array. Why two? Because one would be containing the labels, that is in the numeric representation of the alphabets from 0 to 25, and the other would be containing the actual image input. So it would be the grayscale. So it will be containing 0 to 255 values. So now a couple of things to keep in mind is the first line, the column headers. So we need to ignore it, and each successive line contains 785 comma separated values between 0 to 255. I just told that. The first value is the label, and the rest of the pixels, rest of the things are the pixel values of the image. So here we have tips. So basically we can use CSV reader, so which will return the iterable that returns a row of CSV file in each iteration. So following this conversation, we'll say row 0, it has the label, but row 1 till the end will contain 784 pixel values. To reshape the arrays going from 784 to 28 by 28, we need to use a function, for example, let's say np.array underscore split, or we can use np.reshape, because we need to reshape the values. For the type conversion of numpy arrays, we'll use the method np.ndarray dot s type to float64, or just float. So now we have just yeah, so here we will parse the data from the input. So for that we'll just again open the file. As we can see that input will be given, the same input will be taking here with open file name as file, and then we'll initiate reader, initiate a variable which will be reading the file contains, and then the delimiter will be comma, because comma separated values are there, and then we'll store image and label. We create a two empty list, and then we'll say the for loop where we'll get the first as our label, and then we'll get our data, and that is the values of the images. So we are just reshaping it to 28 by 28 and just appending the whole thing here, and then we'll final reshape, sorry, we will convert it into the float type, everything, and we'll just return it. So I'll just run it here, and here I will just show you one thing, what the labels looks like. Okay, so it will not give me directly the thing, because it will first we need to give the file, and then it will return the images comma labels. So we can see that we have the training images and training label. So now it is time to test our function. So what we'll be doing here is we are checking whether we have properly loaded the training images as well as the validation images, and we can also see the dimensions of our training images as well as the validation images. So we are just passing the training, you can see a training file and validation file which contain the directory where these two are stored, and then it will automatically call this function, because we are calling here parse from data. Then it will get the file, and then it will process, and it will return us the images as well as labels. So for training we will get the training images, and for the training labels, then we'll go for the validation. So we'll get our validation images and validation labels. Then we are printing the training images as shapes. So we will just are showing the shape of the training as well as validation. We can also cross verify the amount of labels that we have. So it is correct. So now what we'll do is we'll just visualize our dataset to get a better clarity of what the dataset looks like. So we'll just run it here and it will, yeah. So here it is, the dataset contains this type of image values. So as we can see here, these are the hand signs, and above is the letter that represent above is the alphabet represents the sign language. The sign it shows, hand sign it shows. So now, so what are we doing in this function is we'll just plotting the 30 images. As we can see, 30 images on 3 rows. So we'll create a function plot categories where it will take the training images as well as the training label, and then we'll just creating a subplot of 3 by 10, and we have given the fixed size and axes are flattened, and then we'll just give the letter is equals to list dot string dot ascii lowercase, and for k in range 30 then we'll give just the image and the label that it contains, and we'll just plot it, and then we'll call the function plot category using the inputs as the training images and the training labels. So now what we'll do is we'll visualize more. So we can also do one thing. This was the one method of calling the data. The another method can be will be using pandas here. This is just for exploring more. So what we'll do is we'll create a variable train underscore df, and we'll call pandas dot read underscore csv, and we'll take the train csv, and we'll just printing the head. So it will return the 5 rows of the whole data set. So here we got the label pixel 1 till pixel 784. Yeah. So now we'll move ahead and we'll just print the columns as we have already seen here, but we'll again just see the columns using the dot columns, and we have label pixel 1, pixel 2 till pixel 784. Then we'll do one thing is we'll just take the value underscore count of the label. So basically what we will get is we will get the number of images, or we'll get the number of counts that are available in the whole set of a particular values. So here we can see the 17 has 1294, while 4 has just 957. So we'll visualize this using the histogram by matplotlib. So we can just do is we'll take the training data dot label and dot hist, and we have provided color as pink and bins is equals to 10, and then we have just given the title distribution of the alphabets and just plotted the short. So here we can say that we are not able to getting the no to the all the labels that we have. It will just give 0, 5, 10, 15. So for more accurate we'll be using Seaborn. So for that what we can do is import Seaborn as an SNS, and then we'll say plt.figure and fixed size is equals to this, and then we'll draw a counter plot, count plot, sorry, where x is equals to train underscore tf dot labels, and then we'll show it. So this has the more accurate representation or actual representation rather than just the histogram. So it will be specifying the each label that we have and their count. So we'll also use plotly for drawing the pie chart for the same. So what we'll do is we import plotly express plotly.express as px, and then what we'll do is we'll take a fig which will be equal to px.pie. We are taking the pie chart and we'll provide our whole training data set, and values would be equal to the train df dot labels and name would be equal to train df dot labels. We'll give the title as count of the alphabets. So here is the count. So here we can see the pie chart and its distribution. So the most label is this one, and the blue is of 3. We can also check verify it from here also. It is 17. So what is it here? 17 has the red one. Yep. So what we can do now is we just did so. Now we'll be creating the generators for our CNN. So now that we have successfully organized the data in the way we can feed our Keras image generator, now we have to code the generator that will yield the batches of images both for training as well as the validation. So some of the important points are here that the image in this dataset comes in the same resolution, so we don't need to reshape it again and again. So we don't need custom target size in this case. In fact, we can't do so because this time we do not use the flow from underscore directory method. Instead, we can just use the flow method. Also, we need to add the color to the dimension to the numpy array that encode the images. If you remember, we did not add the dimensions, whether it is RGB or whether it is a grayscale. We know that it is a grayscale because we can see, but for the computer it doesn't know, for the model it doesn't know, so we need to add the dimensions to it. Uh, Also, this new dimension would be a size of 1 instead of 3 because we are not dealing with the colored images. So in this section, we'll just add the dimension. So first of all, we'll create a function that is train val the generators. So it will create the generators. We'll pass the training images, training labels, validation images, validation labels. So we'll do that, and then we'll take the training images would be equal to np.expand underscore dimensions, and then we'll add the dimension to it, and then um, we'll initiate the image generator class, and we also need to normalize the pixel values and set arguments. Can just add one here. Set arguments to the augmented images if we need. So first of all, train gen will be equal to image generator, and we'll rescale it 1 divided by uh, 255, and the rotation range would be 40. Width shift underscore range would be 0.2, height shift range would be 0.2 again, share range, zoom range would be 0.2, both of them. Horizontal flip is equals to true, and fill mode is equals to nearest. So our train gen is completed. So we'll create the train generator, which will be equal to train gen dot flow. We'll be giving our training images that we have already kept it here, and we'll give the training labels, and we'll give the batch size as 32. The same thing we will be doing with our validation. We'll just keep the rescale to 1 and will not change the other parameters here, and we'll again do the same thing like validation generator would be equal to x equals to validation images, and y would be equal to the validation labels. Then what we'll do is we'll just test our generators to let us know that we have successfully done it. So we are just a second. Yep, this is one. Yep. So as we can see here, we are just now printing the our dimensions of the generators, so we can get to know whether our generator function is successfully run or not. So now that we have done with our data, we have already pre-processed it, and we can now feed it to the our CNN. So this is the last step. We now can create our model uh, in Keras. So it totally depends upon how much layer you add. and what kind of model you select. You can also use pre-trained models such as VCG, ResNet, and many more. But here we'll be creating our custom model. So this is not a very good model, you can say, but it still gives the accuracy of over 90%. We can see that later. So now what we'll do is we'll create a function that will create a model. So we'll take model is equals to tf dot keras model sequential. Then we'll add the first layer as convolutional 2D. Then we'll add max pooling again, and we'll repeat that once more. And then we'll add the flatten dense layer, and then we'll add again a dense. The input size would be here is 226. That would be outputting the labels that we have from 0 to 25. And then we'll just compile our model. Will optimizer would be Adam, and loss would be spare categorical cross entropy. Matrix would be accuracy, and we'll just returning the model. So our model is created. Now we will save our model. So we'll just say initiate with model is equals to create underscore model, which will give our model. It will just write it this way. Yep. So now we can see our model summary. So how the summary, how the model is being architectured. So we can also plot the model. So it will plot the model for us. And now we will train our model. So we'll create a variable history which will be storing the history of our model. So model.fit will giving our training generator, and epochs would be 30. Validation data is equals to validation generator. So now it will run for the 30 epochs. We have to wait for few seconds to get it done. As we can see that in just 10 epochs, we are getting the loss of 0.56 and accuracy of 81%, and well loss of 0.25 and accuracy of that is validation accuracy of 91. So I think we need to run it few more epochs, and then we'll start with the next part of it. Since the data is small, the data set is small, our model will perform quite well here. And in just 15 epochs, we can say we'll get the accuracy of over 90%. You can just see here we already got the 85%. So I guess we need 16, 17 epochs to get the 90 plus accuracy. In the 19th epoch, we can see that we have already almost got the 88%, and now in the 20th we got 89. So likewise, it will be getting above 90 plus. What we can do is we can still change the layer of our CNN to get the most. So basically this is the most basic architecture that we have created here. We can enhance it more. We can also use pre-trained models such as VCG 16 or ResNet, and there are many more models that would directly give us the accuracy of 100% in just less than 10 epochs. So let's check here. So it's been 25th one, and we have almost kind of got 90% in just 24, and we'll get the validation accuracy of 95 here. Let's wait a few minutes to get it done. As we can see that we are almost on the last epoch, and we got 91 plus accuracy in our training, and in validation we have 96, and on the last epoch we got 91.46, and here in well we got 97 and 17. So now we will just plot the accuracy and the loss. So here we are just plotting the validation accuracy versus the training accuracy, and validation loss versus the training loss. So here we are just saying ACC, which would be history of accuracy, and val accuracy would be history val accuracy. Loss would be history of loss, and history val loss, which would be val loss. So epochs would be the range of length of ACC. We can just use any accuracy or loss here to get the epoch that we have, and then we'll just plot using the matplotlib, where epochs we will just give epochs, and accuracy score will give red color here, and label would be training accuracy, and will again give epoch the same range, and will give the well accuracy that we have, and it would be colored in blue, and then label it would be training accuracy. So here it is about accuracy, so we'll give training versus training and validation accuracy. The same goes for loss function, epochs loss red color, label would be training loss. Epoch well loss blue color, label would be training loss. So title would be training and validation loss, so we'll get this loss. So as a reasonable benchmark is to achieve over 90 accuracy for the training, and over 95% of accuracy for validation within 13 epochs. As we can see that we have almost got 91 and the 31, so it is quite good. Try tweaking your model architecture and the augmentation techniques to see if we can achieve this level of accuracy in the lowest epoch that is possible. So that's it, guys. This was all about the hand-sign classification on MNIST dataset. Hope you like this one and you found it interesting. There is the link in the description for this notebook, as well as the GitHub link would be down in the description. And we'll see you in the next one. Thank you. Happy learning.